Yeah, good evening, everyone. So today, we will continue the lecture on value engineering for highway bridges and flyovers. That is a continuation of what we have had last time. So without, so I would like to invite Professor MTR Jaisingh to conduct the lecture as usually. So the all actually is we are happy to. Um, I'm happy to welcome Professor Jaisingh. So I think I don't need to give any introduction. So everyone knows sir, about you. So we will start and we'll continue the lecture. Sir,
Yeah,
if you are ready, you can start, sir. Yeah.
Yeah. Okay. Yeah, it's fine. Right, I'll share the screen. Right, you can see the screen, I hope.
Yes, sir, we can see.
Yeah, okay. So basically, this is about value engineering solutions for highway bridges. So first, I'll give you an overview of the presentation. So we look at introduction, loads acting on a bridge. And when you talk about loading, we have to think about the early British code loading and also the Euro code. The simplest bridge, the slab bridge, and how we can make cost-effective alternatives to the slab bridges. And then how you developed value engineering solutions for a flyover. Last time I explained in great detail, but now today I'm going to show the actual pictures. Last time I have drawn on paper and shown. Today I'm going to show the real pictures. Continued with long span bridges, abutments and foundations, and the delayed ettringite formation. The piers and foundations, pre-stressed concrete, continuous bridges, and conclusions. So we are going to look at all this. And we are also planning another new development, which is still being made. So I will, towards the end of the lecture, I'll tell about that also. So first, introduction. So basically, bridges are generally much more expensive than constructing a normal roadway. For example, now these days, people are coming up with very high figures. So some used to say that, these days an abutment can, 1 kilometer of abutment can cost about 3 to 4 billion rupees, and 1 kilometer of roadway, the elevated roadway, for a 4-lane road can cost something in between 8 to 10 billion rupees per kilometer. So 8 to 10 billion rupees per, say 10 billion rupees per kilometer, 10 billion divided by 360 is 27 million per kilometer. 27 million US dollars per kilometer, which is actually a high figure. Generally, the figure should be somewhere around 10 million US dollars per kilometer is the average cost, but for elevated highways, it can be slightly more. But I can tell you a nice story about elevated highways. So we constructed an elevated highway, that is a flyover of 560 meters long, 17.6 meter wide, 4 lanes, and it was completed and declared open in November 2009. Actually, we started the design in beginning of 2006. We started the design, but then there were some delays in approving our design. So there was about 6 months delay in approving our design by RDA, but then the direct engineering changed, and the new direct engineering took a very positive attitude, had a very positive attitude towards our very innovative design. So he got some young engineers to check it thoroughly, and he got it approved. So basically, our value engineering design was based on very narrow pier, as I explained last time, and the cost was only 550 million rupees out of a 750 million rupee project, where our design prevented the pipe diversion needed by the original design, and that resulted in a cost saving of over 200 million. And as I know that overall cost saving had been around 250 million, but generally when I quote figures, I say 750 million project was completed for 550 million, because there can be some inaccuracy when if I go and say that, you know, it has actually saved 250 million. So what I generally say is 750 million rupee project was completed for 550 million, and which means 1 kilometer of roadway those days should have cost something like 1,000 or 1,200 million, say 1,200 million rupees. So the conversion rate for rupee those days was 120 rupees. So $1 was 120 rupees. So when you say 1,200 million per kilometer divided by 120, so you can get 10 million rupees per kilometer. So basically, elevated highway should cost 10 million US dollars per kilometer. 10 to 12 is very good figures that we can accept, and anything more than that is little on the high side. So when you are, so it's very important for us to have some idea. Then we can also always see whether how much the bridge is overvalued. But one of the things is that you have to keep in mind is when you are doing embankments, the costs can vary a lot, because the difficult terrains, sometimes you come across very, you know, bad lands like, you know, peat, full of peat. Because when you look at our expressways, we have actually selected the traces of our expressways always along paddy fields. So basically, to minimize the land acquisition costs, we have always made sure our expressways go via paddy fields, and because of that, you will get sometimes 3, 4, 5, 6 meters of peat. And when you get that kind of peat, you need special land, the embankment. Before you do the embankment, you need land improvement or ground improvement techniques are needed. Sometimes you go for deep mixing, sometimes you go for dynamic tamping, sometimes you go for various other sand pipe based rapid consolidation techniques. So you have to come up with some solution, and that's where the geotechnical engineers knowledge on advanced consolidation techniques can become very useful. So from our Department of Civil Engineering, we have Professor Kulatilaka, who has a vast experience in this particular techniques, because he was associated with the first major road, a major expressway, that is STDP project, Southern Transport Development Project. He was heavily associated with land improvements or ground improvements from Kottawa to Kurundugaheta section. And beyond that, you know, I think at few sections they had huge developments, and one section of Southern Transport Development Project between Gol and Matara is actually on pile rafts. So basically what they do is pile embankments, not rafts, pile embankments. So basically what you do is at a certain interval, like 3 meter by 3 meter, you will drive precast piles, and on top of that you will cast connected to the properly connected to the pile, you will cast a pile cap. And then you will find that the gap between pile caps is so small. Then you lay a very strong geotextile, and on top of that you will lay ABC. And ABC will act as a kind of a raft which will transfer the load between the pile caps. And then you will construct the embankment on top of the ABC layers. And as the embankment is completed, the whole thing becomes one solid body with piles, pile caps, then geotextile, then you have ABC layer, then you have an embankment. So it becomes a pretty strong foundation for the or a system, not a foundation, it's a system. The whole thing is very strong. So part of the highway between Goal and Mathura is on this type of arrangement. So so basically, so if you look at bridges, they are generally much more expensive than the construction of embankments. And the simplest possible bridge is a slab up to 20 meters. So up to 20 meters, you can use slab bridges. The advantage of slab bridges, you don't have to, if you can have formwork, slab bridge is very cheap. You can simply construct it easily because you don't have any shape, it's just a slab. But when the slab reaches around 20 meters, the thickness becomes nearly 1 meter. Then you will find the self-weight is too much, and it is playing a major role in the long-term development, long-term deflection development. So because of that reason, we like to optimize the slab bridges. And beyond 14 meters, slabs should be post-tension. So we have to apply post-tension. Again, post-tension slabs are not very efficient. So because post-tensioning, the main theory is you have to minimize that section. But if you have a large section, then pre-stressing is not that cheap, especially in the present context where 1 ton of pre-stressing can cost about 1.5 million rupees. It's not cheap to go for slab bridges. And when the slab thickness exceeds 0.8 meters, design may not be optimal. To avoid formwork, slabs have been modified with precast beams and cover up to 18 meters. So this is the typical construction that you see, because that is called inverted T-type construction. And again, because it's like a solid slab, so basically we precast the beams and fill up everything above the precast beam so that it is the inverted T-type solid slab type bridge. But the penalty is it has a lot of weight. So basically, in addition to carry the live load, now the bridge has to carry the self-weight. So that is not very economical. And especially in today's context, it's not economical at all, because in today's context we have to minimize everything. Cement is expensive, the metal is expensive, the manufactured sand is expensive. Then admixtures are expensive. Steel is extremely expensive. So we have to optimize everything. So for long span precast and in situ cast methods can be used. So continuous pre-stressed concrete bridges. Now this is a very special topic. So basically, it's not possible to teach how to deal with reactant moments when we actually design a bridge. It's a special topic. And we are planning to run a training program of 16 weeks for the engineers who are involved in the highway sector, covering the interaction of MIDAS software, dynamics, the structural forms, everything we know. We are going to teach you all, so that you will get an opportunity to work in other countries and undertake projects in countries like Africa and so on, which are actually funded by Chinese Exim Bank. So there are so many projects like that. And if you know the subject very well, there can be many opportunities. So because of that, we are planning to run a complete course where we are going to teach you the use of software and all kinds of things. So this is actually this is a topic that I did for my PhD and completely solved this huge problem that was not solved for 50 years. I actually gave a theoretical solution for this particular problem, and that was in 1989. I actually solved the problem, and 1990 I wrote all the computer programs and showed that this particular method that I developed works very well. And then later I included it in a expert system to show that when you go for artificial intelligence, you need both shallow knowledge and deep knowledge. So that is all. This work is actually something I invented for my during my PhD. And before I sorted this out, nobody knew how to solve this particular problem. So now you can see the new problem. Bridges are supposed to carry moving loads, but we designed them for static loads. So you get highway A-type loading with UDLs and knife-edge loads, and also UDL represents 24-ton trucks located next to each other, where the length of the truck is only 6 meters. So it's little longer than a car, but the weight of the truck is 24 tons. Then when you are talking about weight of a truck, you have to be a little concerned, because the weight of the truck is what you transfer through the axles. So if you look at one of the 10-wheelers that are available in Sri Lanka, Ashok Leyland 10-wheeler, you would have seen that it carries 600 bags of cement. 600 bags of cement means 30 tons. So altogether the truck will weigh 40 tons. And for a 40-ton truck, when you consider HA loading, now you can see that truck is about 10 meters long, because when you consider the passenger cabin, which is also large, and then the large deck, the 10-wheelers are about 10 or 12 meters long, about 10 meters long. 12 meters are the long buses. So Ashok Leyland now has a bus which is actually 12 meters long. And Mercedes-Benz, actually there's a factory in India which is called Bharat-Benz, and that is actually by Mercedes-Benz. They have set up a company to supply all the Benz vehicles to Indian market, and it is called Bharat-Benz. But when they export from that factory, they actually name that as Mercedes-Benz, because all these vehicles have Mercedes engines, but most of the other components are made in India. Mercedes-Benz engines and the transmission all Mercedes-Benz, but rest of the lorry or bus can be the Indian chassis and all that, but to the quality that they need for German-based manufacturing, because they want to reduce the cost of manufacturing. So basically those are very competitive and having large engines, so they are very powerful. So the longest bus can be 15 meters. 15-meter bus means it's about 50 feet long, whereas 12-meter bus is about 40 feet long. And the longest bus available in Sri Lanka is for 12 meter, but the Ashok Leyland 10-wheelers are a little shorter, so it can be about 10 meters. So basically, then you can see with the gaps, little gap that you keep and all that, this 24 ton actually represents a reasonable load, and this is the load that we have designed our STDP project. Southern Highway was designed for 30 units of HV and the HA loading of BS 5400 1978. And there was only one bridge that was actually designed for 45 units of HP, and that is the Orugodawatha flyover that I designed with engineer Himal Chandasiri in 2006. So highway type B loading is to take account of the abnormal loads, and so you can have either 25 units of HP, which means 1 unit of HP means 1 ton per axle. So there are 4 axles. So 25 tons of HP means 100 tons. whereas 30 units of HV means 120 ton vehicle, and the length of the vehicle can vary, but the shortest vehicle is having 6 meter gap between the front and rear axles, and the distance between two axles is 1.8 meters. So 3.6 plus 6, altogether the length of the vehicle is about 10 meters. So over 10 meters, we are talking about a vehicle having a weight of 120 tons. But in countries like England, they always design the main expressways for 45 units of HB, which is representing height 180 ton vehicle. So when you look at this kind of loading, now you feel very confident, because the bridge has been designed for a load of 120 tons, but the lorry carrying the maximum load that will act on the bridge is only about 40 tons. And on top of that, you apply so many factors of safety. So the overall factor of safety, when you consider the material factor of safety and all that, the factor of safety is about 2 or little more than 2. So which means, even when you have a 360 ton vehicle on your bridge should be okay. So the moment you know that, you get a lot of confidence. Why? Because we know even if we make a slight mistake, still nothing can happen to the bridge, because it has been designed to carry a load about 300 tons without any problem, whereas the maximum load you are getting on the bridge is about 40 tons per vehicle. So only thing is, when you have this kind of very heavy vehicle, we don't try to put a lot more other vehicles on the bridge. But in the normal range, it doesn't matter actually, because when you have these short bridges, anyway, the HV load can dominate. So because of that reason, whatever the number of HP units that you use may be the dominating factor. So modern codes can have slightly modified versions, and the net effects can be 20 to 30%. So basically, this is the chart that we use for BS 5400 1978 code, and this is the chart that has been used for most of our existing bridges. And also, I am not very sure what they have used in Central Expressway, but I know for most of the other bridges also, and other expressways, they use this particular chart. And this is the HB vehicle, and we can see this length can vary between 6 and 26 in increments of 5. So we can get 11 meters, 16 meters, 21 meters, and 26 meters. So basically, the shortest vehicle can be about 10 tons, 10 meters of length. Now, then later, somewhere in 2006, the British codes were amended to include this particular agreement. Early, it was going flat here, somewhere here, going flat. And then they said, no, it cannot go flat. It has to increase to a huge value, like 200 kilonewtons per meter. So basically, this was to allow, there's a tunnel between England and France. And what happens is the trains are so big that the trucks can be loaded onto the train and then taken to England. So on the other hand, the trucks can be taken to the ferry as well. So basically, when lot of trucks in the continent or European continent are allowed into England, they found that those trucks are actually heavier than that they anticipated. So because of that reason, they amended these laws. And then when it comes to European laws, they are a little different, because we are applying the lane width is limited to 3 meters. That's the most important thing, because in the earlier British code, they allowed a wider lane width, whereas in Euro codes, the maximum lane width is 3 meters, so it's fixed value. And then what they say is, if you have to load at least one lane with 9 kilonewtons per meter squared, which is pretty close to HA loading, pretty close to HA 1978 loading. And then all the other lanes should be loaded by 2.5 kilonewtons per meter squared. And in addition to that, they can say tandem axis or single axis or single wheels. So basically, along with this load, you have to apply some of these concentrated loads as well. So those are these axes. So these loads also should be applied. And then they also have other abnormal vehicles, and abnormal vehicles can be a vehicle like this. And there are different levels of abnormal loads, and depending on the risk factors involved, you have to actually come up with a reasonable value for abnormal loading. So we have to decide at which level that we apply the abnormal loading, because that all depends on the type of vehicles that we are using in our roads. So if you are applying an abnormal load, so if the total weight of that abnormal load is about 150 tons, that may be a reasonable selection. So you have to actually look at the specification that has been selected by Road Development Authority and do the design according to the load specified by Road Development Authority, considering the type of loading that will come onto the bridge, because Eurocode allows so many different levels of loading. So we have to come to a conclusion that we are going to do all our designs for a particular level, but that particular conclusion has not yet been reached. So RDA is yet to announce that, hereafter we are going to use this particular set of loading for Sri Lanka. I think still RDA has not announced which one they want to select, but we have done few comparative studies to show where we stand. And even recently, one of the engineers from Road Development Authority, engineer Ajit Abesuria, he's a fairly senior engineer. He's about 56 years of age. He did his MSc and he did a complete comparative study. So several comparative studies are available for us to make a decision, but still RD has not finalized anything. But whatever they specify, we have to use when you are developing the bending moment and shear force diagrams. So once you have the set of loading, so basically the abnormal loads, the magnitude can vary from 600 kilonewtons, that is 60 tons to 360 tons. So you can see in the earlier British codes, it was 180 tons. So you have to, now Euro codes are going lot more, can be lot more than what is specified in the normal British code. So, but in a country like Sri Lanka, where we are not getting very, very heavy loads, it may be okay to go for something like a range like 150 ton overall vehicle weight may be reasonable, because our maximum loads are in the range of 40. Now this is a very important statement, and this was said by engineer Robert Benham. And Robert Benham has actually written a book. He's a very, very practical structural design engineer for bridges. He's a very practical bridge engineer, and he ran his small practice. He had a small company, but many big contractors used to go him for turnkey type projects, because his solutions are very economical, and we know him. So concrete bridges designed to our codes of practice. Actually, he said this in Cambridge University on 11 July 1990. Concrete bridges designed to our codes of practice are at no risk of failure due to longitudinal actions under the specified traffic loading. The search for excessive accuracy in the calculation of transverse distribution of moments due to live loads, for instance, is a waste of time. So what he basically says is, because we are using very high loads, don't try to split hair on the bending moment value that you get. So if you get a reasonable bending moment value, just continue your calculations, because the bridge is never ever going to fail due to a minor error in the maximum bending moment that you have calculated. So you don't worry too much about it. It is far more preferable to think carefully about the stresses which can arise in the car's in situ bridge deck during construction due to temporary conditions, high initial pre-stress forces, settlement of foundations, and above all heat of hydration effect. So this is what these bridges were Southern Highway STDP project bridges from Kurundugahatanme to Matara were designed by the local engineers at CCB, and they did not pay enough attention to this, but they paid a lot of attention to this, but not enough attention to this. So because of that, we had a huge problem of pile caps cracking. The reason is the amount of reinforcement provided was extremely low due to some misunderstood calculation. So because of that reason, we had huge trouble because there were so many cracked pile caps in that particular project. So basically at the preliminary design stage, the designer gets most of the important parameters like number of spans, length, and so basically Professor Tim Abel is actually our former external examiner. He's a good bridge engineer, and he's currently the Dean of Faculty of Engineering and Design of Bath University. And he says it's a fun part of design, but that is the part where you can get things drastically wrong as well, because you are making the vital decisions at this stage. So one of the vital decisions that were taken as a wrong decision in STDP project was they decided to have the bridges on precast pipes. Generally, if a river is involved, we generally don't go for precast pipes for the bridge, because precast pipes can be very much affected by scouring. And sometimes you will find that, there's one bridge at Mahavali River. So they have actually constructed the bridge longer than necessary. But in one of the flood seasons, the bridge, they found the river found that the bridge is too short, and bridge went behind the abutment, and then they had to construct another bridge because now the river has suddenly become too wide for the existing bridge. Actually, existing bridge had one extra span, but even that was not sufficient. So because of that reason, generally for river bridges, the bridges over rivers, we actually go for we don't use precast piles, we use board piles, because board piles can be properly anchored into the rock. Whereas in Southern Highway, most of the bridges are on precast piles. And then when you are using precast piles, you have to think about the lateral stability of the bridge. Now that is also a major problem, because you have precast piles, you tend to think, okay, if the bridge is not stable, let's have a battered pile. Battered pile is a pile driven at an angle that you can easily do with precast piles if the soil is weak. But battered piles perform very poorly in earthquake situations, and if the battered pile is damaged, then the whole bridge can collapse, because the shaking can be too much for the deck to be stable. So because of that reason, we never use battered piles, but in Southern Highway, we found that they have used battered piles as well. So that's why, you have to be very, very careful here. You have to read a lot and learn the pitfalls in bridge design, and then be ready for those, so that your designs will have minimum errors, because these are fundamental errors. You make the wrong selection, fundamentally wrong selection, and then nobody can correct it. So our Southern Highway up to Matara, from Kurundugahatam, have a lot of mistakes. And by the time we were invited to review, most of those have already been completed. So because of that reason, we could not change. But anyway, for some time, I kept on insisting that all the bridges having problems must be demolished and reconstructed. But our biggest problem was the contractor submitting huge claims when the work is delayed even by 1 day. So we had a huge problem because the contractor, Japanese contractor, was actually trying to squeeze everything out of Sri Lanka. So because of that, we had to work with some even the experts from other parts of the world, and one way or the other ensure that the road is open to traffic as early as possible, because every single day meant more money for the contractor. So we had to we could not delay it to get it sorted out. So we had to repair the damages and get it sorted out. So that was the situation in Southern Highway. So basically you have to be very careful in contract management, and if you don't do it properly, you can have massive problems and the contractor can go for massive claims. So you have to be very vigilant when you are doing contract management, and you must know the exact role you are playing. If it's a turnkey project, you are the client, you don't say anything to the contractor because there's a consultant and a contractor. So you don't tell anything to the contractor, but you observe everything done by the contractor. And if there's anything that you don't like, you write a letter to the consultant and tell him, we have observed this kind of problem, and please pay some attention, and we like to know what is your response to that. So you fix the consultant and you don't speak to the contractor, because if you ever speak to the contractor, the next day you will find now a letter from contractor saying, you have requested this particular piece of extra work, and we have talked to the consultant, and consultant is also agreeable, and because of that we are undertaking, and then and the charges will be notified later. And by the time charges come, you will see charges are huge, because now the client has been trapped. So because of that reason, you have to be very careful when you do contract management, and you must know where you stand and use your authority in a very shrewd manner. Otherwise, the contractor will always find a reason to submit a claim and make a massive gain from the fixed price contract. So you have to be very careful in that sense as well. So try and understand the principles of project management. And in my case, I have handled so many projects, so we know how to handle the contractors. And generally contractors also know that we know the subject. So generally they never try to make claims when we are involved. So in future, most of the well-written computer software will be able to handle the detailed design part is actually now handled by most of the software. So when you use MIDAS civil software to design a bridge, once you get this part correct and then make a proper mathematical model, the rest is almost automatic, because the program can analyze, can perform the analysis, and then the program can actually do the design as well. So programs are very powerful these days. So that's why getting this part of the project proper is very important, because if you don't get this right, then this can be rubbish. So that's why we say garbage in, garbage out. So unless you get the project proper, you can have many problems. Right. So then, so let's look at how to optimize a bridge. So when you have a bridge, what happens is, we all know, let's assume that it's a slab bridge. Then we know for sure, in a slab bridge, about 80% of the concrete is cracked. Any concrete below the neutral axis is cracked. So if you're having a cracked concrete, it is not doing anything useful other than protecting the steel. So if that is the case, then remove that cracked concrete. and replace it with a single beam, and remove that contract control and replace it with a single beam. And then rather than, this part in compression, so you will create a thin slab that will span between the two beams. So the moment you do that, you are removing this concrete, this concrete, this concrete, and all these massive concretes. And then you find you have removed a significant portion of the self-weight of the structure. And self-weight is a penalty that you have to always carry in a bridge. So because we are not interested in carrying self-weight, what our interest is to carry the live load. But to carry the live load, you have to have a structure. The moment you have a structure, you have a self-weight. So because of that, we must minimize the self-weight. So the ideal way to minimize the self-weight is going for this type of modification. And I can show you the modification. I'll show you in a moment. Right, so the bridge is actually constructed like this. So the bridge comes in with a beam, and to assure that the beam can be complete, the bridge can be completed without proper formwork, what we do is we cast the slab in 2 stages. So the top slab is cast in 2 stages. So first we cast a thin beam, and from this beam we can have some 2 supports, and one way or the other we support it, and then pour the concrete, and then make it all continuous, so all combined. So basically composite beam. So we precast this beam, place it, then we precast a thin panel, one way or the other support it, and pour this top concrete. So the top overall thickness of this concrete will be about 200 to 225 millimeters. So 200 to 225 millimeters will be the thickness of the finished completed thickness of this slab will be 200 to 225 millimeters, and it hardly goes up to 250 because we are so concerned about self-weight. So if you think 225 is not sufficient, you will go for 230. So that's how we change the thickness of the bridges, because anything that you lay on the bridge which is not contributing to the load carrying capacity is a penalty. So because of that reason, we try to keep all the members as thin as possible, so that when you look at it, you might find sometimes, most of the bridges, the self-weight is about twice the live load. But in this particular case, it can be even about 50% of the live. So you can see it's a huge gain you can make. And what we do is we actually complete the bridge in several phases, but most of it is precast. So basically, the moment you have a crane, then you can easily place these beams. Even without a crane, only the heavy beam is on this beam. Other beams are not heavy. So what we do is we simply precast everything and then make the bridge like this. So once you make the bridge like this, you can actually create a grillage, and this is because in the grillage, each of these beams will represent one of the longitudinal beams. So one of these beams will be represented by these beams. So this way, you can actually construct a bridge at a very low cost. I actually used to construct this method to construct 300 feet long, 12 feet wide bridge at Mahayangana Rajamaha Vihara, because there's a small reservoir in front of the temple. And during 2011 or 11 or 12, that era, 2012, 2011, they actually, the irrigation department wanted to rehabilitate the bridge, to rehabilitate the reservoir. So during that time, the police wanted to create an artificial island. So we had to connect the artificial island with the bund of the reservoir. So the length of the bridge was 300 feet, 12 feet wide. So it's a fairly large bridge. And the cost was only 6 million rupees in 2012. And it was all completed in 2013. So the cost of the bridge was only 6 million rupees. and it was like 2,000 rupees per square foot. And if you have asked RDA what is the cost of constructing a bridge, those days they would have easily said 20,000 rupees per square foot or 200,000 rupees per square meter. This was in 2012-13 era, so nearly 10 years ago. That was the cost. But today, if you ask an RD engineer, they will give a much higher price. But you can see that using these methods, you can actually reduce the cost very much. And this is the long bridge, and you can see when you go there, just go and have a look. It's a wonderful maintained bridge, and its scenery is very nice. And so you can see this is what you see inside the within that artificially created island, and even the foundation of this structure was done by me. And then there's another Buddha statue coming up of 84 feet height. And so basically to help you, we have done research, and we have done so basically depending on the span, now we have a chart, and you can straight away say what is the thickness of the beam, and then even the reinforcement has been calculated and then converted to a chart. So by using this chart, within 5-10 minutes you can complete the design of a bridge. The design of a bridge can be completed in less than half an hour. You can give the solution, because all the information that you need have been converted to a chart. And then that the student who did most of this work, they were all from Jaffna, and they did now the guy who developed this chart, or there's another chart that he developed. So all that particular student is in Australia now. He has done his PhD. He got a first class, and he has done his PhD at Queensland University of Technology. After that, now he's married and he's living in Brisbane, Australia, working for a large firm that is specializing in, I think, fire engineering or facade engineering. I think, yeah, he's a facade engineer. So he knows how to design very large facades. So he's a facade engineer, and he's specializing in that particular area in Australia. So basically you will see that most of the top work in Australia is actually done by Sri Lankan engineers. So basically this is the first type of bridge I told you, the not so efficient, because they are so heavy, and because of the weight they are not economical. So then to make it better, they went for this particular one, and here you can see it's hollow. But later, they went for this particular bridge, because in this one you cannot inspect what is here, cannot be inspected. So because of that reason, they found it's better to go for this type of beam, where the beam need not be placed touching each other. They can be placed with a certain spacing. And so you can see Y beams at 1,000 centers and Y beams at 2,000 centers. So Y beams at 1,000 and 2,000 centers. So this is actually 1,000 centers, and this is 2,000 centers. So you can see the 2,000 centers one. The maximum span is limited. Maximum span is limited to about 20 and a half meters, whereas this can go up to about 31 meters. And the section properties are also given. So basically all this information can be downloaded on internet. Otherwise you can make use of this particular lecture. So Y beams are cast like this so that you can do the inspection to see whether any damage has occurred to the structure. So if you look at flyovers in Sri Lanka, so this is the flyover on Kandy Road at Paligoda, and you can see it's now this type of flyover. The cost was 800 million rupees, whereas it is only a 2-lane flyover. The length is generally around 300 meters, so the cost was about 800 million. whereas our half a kilometer long concrete structure cost us only 500 million, 500 or 550 million. Whereas this 2-lane one with a shorter length has cost 800 million. So that's why you don't like all these unsolicited type deals, because there's no transparency in that type of deals. So this is another view of the same bridge. And this is the bridge, again a blunder, big blunder here, because this bridge is not meant to be constructed over the sea. And this is the bridge at Punarin that is called Sangapudi Bridge now. But this was actually meant to be the Panadura flyover. This is the Panadura flyover. But due to some reason, they found that, constructing a bridge across the sea at Punarin, connecting Punarin and the Jaffna Peninsula at called Sangapudi Bridge is more important than having a flyover at Panadura. And if you are a politician, you might say, oh, we wanted to have friendship and this is the bridge of friendship. But unfortunately, the bridge of friendship must have galvanized steel. But in this particular bridge, it's not galvanized, it's just painted with marine paint. And because of that reason, what happened to Mathara Bridge, Mathara Cable Stayed Bridge, can happen to this one as well. Mathara Cable Stayed Bridge was galvanized, but nobody looked after it. So it started corrosion. Nobody wanted to have a look at it. And one day it collapsed. So you know the story of Mathara Cable Stayed Bridge at Mathara. I'm sure you know the story. And it was actually designed and constructed by State Engineering Corporation, and they used galvanized steel everywhere. But unfortunately, nobody wanted to look after the bridge once it was completed. So even with galvanizing, corrosion started, and one day it collapsed. Fortunately, nobody died. And this is the Orgodawata flyover, and you can see it's a 4-lane highway. And so this is the cross section of Orgodawata deck, and RD design had so many beams, so we reduced it to only 4. And this is the Mattakkuliya Bridge. So the Road Development Authority's design structure was pretty identical to this Mattakkuliya Bridge, which was completed somewhere around 2002 or 2003. And because still it is not very much used, I think now it's okay, because the access roads were not very good. So this is a section of Mattakkuliya Bridge. And this is a bridge that I designed in 2009, January or February, for Maga Engineering, because the original design by engineer Chandrasiri had a raw foundation, but Maga engineers thought, okay, better to go for a deep foundation. Because this is a place where, as you can see, the sea is on one side, the lagoon is on the other side. So this is like a causeway. So they thought better to have a pile foundation than a rock foundation. So it's a bridge with 25-meter high girders. So I actually designed this bridge. It took me only 4 hours because I was using a spreadsheet. So I designed this bridge in 4 hours, or less than 4 hours, by using one of the same spreadsheet that I use for designing the Orgodawata flyover. So I was paid 2 million rupees initially to complete this, and then I completed the next bridge, which is again having 75-meter long length, and I was paid another 2 million. So I shared all that with the structural design engineer, Engineer Nuansena Kavanagaratna, who was the chief structural engineer at Maga Engineering. So once I designed the beams, I just gave it to him and said, you look after the rest, because he was an expert tall building designer. And I told him, okay, this is how you do the design. And he simply perform the structural design. So my contribution was actually optimizing and getting the deck proper. So still the bridge is there, and it was completed only in less than 4 months of operation. So it was all very fast construction. And so basically we discussed these loads. So when you are doing value engineering, this is the example that I have already explained. So I will not explain it in great detail, because at the beginning I explained all these facts, and the facts here can be very slightly different what I explained you, because what I gave you today can be a more accurate picture than what I have written there in 2017. So this is actually a 2017 presentation that I made when I wanted to do a value engineering lecture at Bath University, England, for the lecturers of that particular department. And this is the section that we use for the bridge. And today, even more elegant bridge has been is under construction, and that is at the Slave Island. At the Slave Island, you would have seen a huge construction going on, and it's all by Maga Engineering. So the chances are that it will all be completed very soon. So when you are providing reinforcement, you have to be very careful, and you have to ensure there are chamfers, and chamfers are provided with extra reinforcement, and so on. So basically, you can see they are using rubber tube type technology, and they, after completion, they pull this out, and then they will put the tendons and do the grouting and make bonded tendons. So you need to have end sections like this to distribute the loading, and you will use this kind of large jacks. And, so basically, generally the strength of the strands is 1,860, and generally we don't go beyond 75% when you are initially stressing. We're going up to 80% may be a little too much with the steel is coming from India. Generally, don't go beyond 70%. But if it is a very highly reputed manufacturer, and then you can go up to about 75%. And these beams are very heavy, about 150 tons. So you have to have special arrangements for steel arrangements, and then jacks, lifting equipment, all kinds of things are needed. And you can see the kind of lifting equipment they have been using. And then when you launch it, you can have a railway line on it, and then you can bring other beams as well. As I explained, the deck slab can be about 200 millimeters, and generally the minimum reinforcement in a deck slab is at H12 bars or QST bars of 12 millimeter at 150 centimeters. Generally, don't make it bigger than that, because if you make it bigger, the durability can be reduced, because they can be flexural cracks. So if the flexural cracks are wider, the durability will be lower. So because of that reason, we use H12 at 150 centimeters. And then you can see the kind of massive deck that you get, and you can see there are gaps between the beams and so on. And this is that earlier A4 road bridge, two bridges that I told you, 75 meters and 125 meters. So this was all, you can see, very nicely constructed structures. So plate girder bridges, then there are many other bridges, box girders, and these days Maida Civil is available, so you can model any of these bridges. But the most important thing is to get the first design right, the concept right. So for the concept, I'll show you a few things, and after that, these are just analysis. Anybody can, with little knowledge on software, can do this type of analysis. So I don't consider it as a major thing, because in my case, I sometimes just use my own rules to find the bending moment, and when I find that value, I generally find after spending so much time, the engineers come up with the same answer. I also get bending moment diagram like this, the shear force diagram, the torsional moment diagram. So there are so many moments that you have to consider. And then the next important thing is we have a major problem when you have joints. So one classic example is the Panadura bridge. So the expanded joints were very annoying in that bridge. And with the experience that Road Development Authority has gained over a period of time, now they have decided we are not going to worry about these expansion joints anymore. We put a geotextile and then we'll do a carpet on it. And if the joint fails, we'll just repair it. But we cannot be worrying about these joints, because the joint can allow seepage of salty water, where the salt is used as a de-icing salt. So the moment that happens, these bridges can undergo chloride attack. So because of that reason, these days we don't like all these expansion joints. We simply correct the expansion joints with one of these methods, and the method that we widely used in Sri Lanka is this particular method. So this is the type of method we used in Sri Lanka. Or basically this is more like this method, because we actually, in this method, we are using slab as a continuous method, poli load, whereas in this method, we are not doing that. We are having simply supported joints where they are all connected. So the whole idea is, no water leaks through this particular one, because you can put a geotextile at this level and ensure that no water goes in. So this is the type of joint you get in a bridge. And so after 15 years of usage, if you properly do that kind of joint, you will never see the joint again. And then you will need the road, the foundation for the bridge, the pile cap, goes also with the foundation. Then you need the basement then you need the pier construction, and after the pier you need the pier cap construction, and then you need the deck construction. So you get the foundation, substructure, and superstructure. Superstructure is beams and slabs, whereas what is in between the pile cap and the superstructure, including the pile cap and the piers, all will be called the substructure. So piers and pier capping beams all are called substructure, whereas anything above the pier capping beam is superstructure. So basically, so these are the ones where you can get huge problems unless you get it right. So I'll go show you one thing. This is the flyover on A4 road, A2 road at Hambantota. That is Colombo Vallawaya road via Hambantota, Matara Gol Matara Hambantota, and this is the crossing that is available at the Mirijivilla and the A2 road, and this was I had to go there for some problem associated with foundation, and so this is actually reinforced earth, where the earth is used as a retaining material by having precast units and then some ties this way, so that the precast unit will not get too much load on it. And this is called reinforced earth. And these are the reinforced earth pallets, and these are the reinforcing strips that are buried in the soil. And then when you have abutments, you can have run-on slab as well. And here, if you look at this drawing, you can see it is having some kind of a slab. so that even if the soil settles here, still the ride will be perfectly normal. This is the foundation at Hambantota, because they had bedrock at very close depth. So because of that reason, rather than going for pile foundation, they went for a rock foundation. And that is fixing, and you can see the kind of reinforcement in a pile cap. The pile caps are generally very heavily reinforced. And if you see a pile cap which is not heavily reinforced, there can be something wrong, because if the DEF comes, that's the end of the story. And this is the pile cover and all that, concreting, and this is what happens if you don't get it right. And I'm sure you don't like this kind of cracks in a structure that you have designed. So the way that you prevent this kind of cracking is by controlling the placing temperature of concrete, and also using low amount of cement with very low water cement ratio, so that you get super high strength concrete. And if you are not sure that this will work, then we can use steel tubes buried inside the concrete, and then start pumping water, so that all the heat energy generated within the pile cap can be removed by using a pipeline like this. And we actually used a pipeline like this for few box culverts that we designed between Goal and Martha. So we actually designed 47 numbers of box culverts between Goal and Martha. And it was by my team, so I also had a huge role in that. But all the design calculations were done by, and the modeling was by other lecturers whom we discussed and taught them how exactly should be done. And then, there are software that have been developed to predict the kind of temperature increase. And by using all those software, we actually developed a set of curves like this. And to download this particular paper, go to Google and type MTR Jaisingher and DEF, and you can download the paper. And there's a Syria report involved, Syria 606, and that report also can be downloaded from internet. Syria 606 report by Professor Bamforth. Bamforth is from Imperial College London. So then Pierce, not much chance of optimizing, but you can make it smaller and like this, and then you can actually have huge cantilevers from this place. So it is 5.5 meter cantilever. But if you look at the way that the reinforcement is provided, not yet only the reinforcement. Now here you can see the placement of pre-stress index within the pile cap. And last time I showed you how we do the two-stage pre-stressing, because if you apply too much pre-stress here, what happens is it will crack here. So you cannot have too much pre-stress, just the sufficient pre-stress to keep alive. And then once you place all these beams, the loads are again acting downward. Now they have to pull and make sure the edge goes up again. So when you place all these beams, this will go downwards. Then you pre-stress and put it back. So that way you can have very lean construction. And here you can see kind of situation here during construction. You have to be very careful when these people are moving, because if they move in the wrong direction, you can have problems. And so this is the underneath, and you can see some of these 150-ton bridge beams are actually placing outside the pier capping beam. They are no longer supported by pier capping beam, because all the load transfer will take place via this due to the pre-stress. So bridge decks, you have to go for good materials, because bridge decks have to be super durable and should last more than 120 years. So always go for high strength concrete, and I have already explained how to obtain high strength concrete by carefully controlling the water cement ratio. And sometimes in future it might be very much cheaper to go for side mix concrete rather than bringing the plant mix concrete, because everything is so expensive, diesel is expensive. So the moment you try to transport the same thing twice, it will cost you a lot of money. So it's much cheaper to get everything uh, to you and do the site concreting, so that you can save a lot of money, because a diesel liter can cost around 500 rupees, and these lorries are not very efficient because they are carrying huge loads. So because of that reason, it's better to make sure that the site mixing is done. So basically, I will not cover this particular part. The reason is it is a very important aspect, and if you are interested, let me know. I will try to teach it, but that is actually a fairly advanced design method, which is not used anywhere in any bridge in Sri Lanka, and you can find some bridges in America and UK designed with full continuity, but it's not a very usual case. It's a very complicated case, so there's no point. We are not going to gain much by learning that. And if you come and follow our MSc course, you will definitely learn the art of designing the continuous bridges. So it's I have a spreadsheet and I can design bridges very fast, but it's based on a particular theory. To understand the theory, you have to struggle a little bit. So we're not worried about that. So the conclusion is design of flyovers and bridges is a challenging task, because you can't be a building engineer and then suddenly become a bridge engineer. If you want to be a bridge engineer, work in few bridges, gain confidence. And in my case, I started working at a bridge site when I was how many years? 21 years old. It was in 1984. I was heavily involved in bridge construction. I was only 21 years of age when I was constructing the Kadwela Bridge. And I was a trainee, second year trainee, and we were very actively involved in the Kadwela Bridge. Though we had our training station at IESL, we got the permission because we are very keen on learning. We spent around 2 weeks at Kadwela and learn everything about concreting and pre-stress and everything we learned. So basically, it's very important that you should have spent some time at a bridge site. Don't become a bridge engineer without going to a bridge site and spending some time at a bridge site, because you can learn a lot. And then we went to see how the Kalutara Bridge was constructed. So then I did a PhD on bridge construction, and then my wife was also designing bridges. So we are actually masters of bridge engineering. And then after coming to Sri Lanka, I thought, I should learn tall buildings as well. So that's how I'm a bridge engineer turned to a tall building designer. So today we can handle anything. It can be bridge, space truss, super tall building. You tell anything. Nothing is a big challenge for us. We know how to handle any kind of design, and also we have really good value engineers. So any project that will cost 4,000 million, we'll do it for 1,800 to 2,000 million. So we can always optimize bridges with all these techniques I have told you. Only thing is you have to read and get it to your mind so that you will get the courage to do value engineering. Doing value engineering is not easy. You must have thorough knowledge, because you are going to optimize the design of an expert engineer and to come up with 50% of the cost of that particular project. It's not easy, because you are challenging one of the top engineers in the country by when you are doing value engineering. So you have to be a master of the game. So I have given you everything, how to think. but it's up to you to practice these things and come up with something. And so before I actually go into the final part of conclusions, I would like to show you something, and that is about how to construct bridges without using reinforcement. And I would like you to think about the bridge with 7 arches or 9 arches at L, and L railway. We have stop share. Right, okay. So basically, today we have a big challenge. So challenge is reinforcement is very expensive. So I'm actually planning to use this kind of arrangement. So this is a big beam, small rib, and then you will repeat it, and then deck to be arched shape. So there will be forces coming this way. These forces will balance, no problem. This will not balance. So because of that reason, we'll need some kind of strengthening. So this part of the bridge can go into tension. So I'm going to use bamboo reinforcement because I cannot put steel inside the soil. So I'm going to use bamboo reinforcement because bamboo is not going to perish. So this doesn't need much width. So 300 may be enough. But here I'll put a massive width like 600 to 700 millimeter. But beyond that, this is all cement stabilized earth, and I might have some bamboo running this way. So this is something that we are actually doing some research at the moment, and this all will be arch. So longitudinally arched. This is also arched. So everything is arched. Arches are masonry structures subjected to compression. So if you can ensure the whole structure is subjected to compression except at few locations, then there are many other solutions. So one of the solutions is you will use some reinforcement. My thinking is I should not use any reinforcement. So the other method that you have is you will cast some small concrete, reinforced concrete beams, or you can even apply pre-stressed concrete to that, and then just bury it. So when the loads come, this will, and then what you do is when the loads come, this will be okay, because if there are some members that can take tension, this side can take compression. So because of that reason, you will find it works fine. Or otherwise, what you do is this beam, although it looks straight, you will not cast it straight. You will cast it with a slightly arch shape. So the bridge will have some kind of lateral restraint here. So these arches are pushing it this way. So you make it a slightly arch shape, and the deck can go beyond this point. So because when you have arch shape, and if you have some small component going that way, it's not a major problem, because you can put some bamboo reinforcement in that level. So one way or the other, you can actually do a construction of this type, so that almost everything is arched. And the moment you have an arches are very good in carrying compression. So because of that reason, you can easily construct bridges without using any reinforcement, no QST bar. So that is the next challenge I'm planning to take. The final year project is now run. So the idea is we'll make a bridge at Moratua. So only thing is funding. We have to find some funding. So we are planning to ask IESL has 400 million rupees in accounts. So what he says, set aside 5%, give us a loan at whatever the interest rate that IESL gets from the bank. IESL can deposit this money in the bank at 20%. So give us a loan at 20% interest rate. So we'll pay the loan back, because this is the time that we have to support research. Because unless we do research now and come up with new methods, we are never going to come out of this mess, because everything is so expensive due to this Russian-Ukraine war. So this is the time we must come up with new methods, very new methods, and thinking completely outside the box. We must come up with all these methods and solve the problem. Otherwise, nobody's going to solve our problems. So I'm going to share the screen again. So basically, the self-weight is the biggest challenge in a bridge. So if you can come up with the method to reduce the self-weight of a bridge, that as we do with box girders and all the other things, then the cost of the bridge can be reduced. So that is the theory, and that theory is very much applicable today, because today concrete is expensive, steel is expensive, formwork is expensive, and so even the labor is expensive. So the moment you go for something that will reduce the amount of material, automatically the labor component will also be reduced, because more material means more labor. So less materials means generally less labor, not always, but generally less labor. So you must try your best to come up with less labor, less material, less reinforcement, less pre-stress. Everything should be reduced. Then the moment you do that, you will be having a good solution, and that solution can be a value engineering solution. And the beauty of value engineering is you are entitled for 10 to 30% of what you save. But to be reasonable, we can charge only 10%. But there are engineers who have charged 50% of what they save as well in the past. And many engineers go up to about 30% when they do value engineering. So with that, I will conclude. So if you have any questions, you can ask. Otherwise, Prima, so you can decide what to do. But I want to do an acknowledgement. So that is, Professor Chris Burgoyne. So we are having some disturbance, Trima, I think you will have to. So Robert Benham of Robert Benham Associates, Mr. Engineer Dantanarayana, he's a very experienced engineer who did the Orugadwata construction, and then he was associated with Outer Circular, then he was associated with Mataramattala. Now he's about 75 years of age, and he prefers to stay a little away from construction, but he's a very experienced engineer who worked until 2020. He worked until 2020, and because of his various minor ailments, he likes to stay away a little bit. And Mr. Chansiri is one of the best I have ever seen structural engineer. He's a fantastic structural engineer. He knows structural engineering so well. He can design any bridge on a half sheet or two, and he's the best I have ever seen. And Mr. Mangala Silva, Mr. Mangala Silva, he has done a lot of drafting for me, because when I undertake large things, I always ask him to help me with drafting, because I'm not good in using AutoCAD, but he's a master of it, and I don't trust draftsman sometimes. Then I ask him to help me with all the drafting work so that he also can gain something. So he did all the drawings of Orugodotha flyover. He did all the 47 structures of Goal Mathur extension, and he has done so many other drawings for us. Though he's an engineer, he's a master of AutoCAD. So sometimes when we work in a team, we ask him to do all our drafting work because we don't want mistakes in our drawings. And Engineer Rohita Sarna, former Director Engineering, and also he was the Director General of Road Development Authority for about 2.5 years. He actually became the Director General after Engineer Chandasiri retired, and Engineer Chandasiri is 7 years senior to us, and Rohit was 5 years senior to us. But I have supervised the MSc project of both of them, and contract of Orugodotha flyover, Maga Engineering and Access Engineering. They all have helped us, and then all these lecturers, professors from Bath universities, because we have a lot of contacts with universities in England and America. So that's why we basically say our engineers always end up in doing their PhDs in one of these countries if they are good. So this is a question time, and Trima, I think it's up to you now. Over to you.
Yes, sir. So, participants, so if you do you have any questions, you can ask if you have any questions.
Chat had something, but now I think it's gone.
I think, sir, now the time is also 8:30.
Yeah.
I think so. We'll conclude today's presentation.
Okay.
So as usual,
one word. Basically,
yes,
all the participants have to recall what they have seen in the last lecture. So first, because our recordings are available, first go through the first lecture, then go through this one. Then you can understand it better. Although it's a presentation, going directly into this, you can understand something, but if you want to understand the real theory, always go through the earlier presentation, last Thursday presentation first, and then come to this one. Okay.
Right. Okay, sir. So thank you very much, Professor. So usually, so you are sharing your knowledge with us. So there is a request from the chat box that to share the presentation. Of course, we will share the presentation soon as possible. So thank you very much, Professor.
Trima, yeah. Can you actually make it available to Imanta also, so that he can put it on I also have this advanced computer modeling of structures channel, so we can include in that channel also, so that more people will have better access to the presentations.
Right. Okay,
you can
sir.
send it to Imanta, it's a great help.
Right. Okay, sir. Okay. Right. Thank you very much, sir. So we highly appreciate you sharing your knowledge and you spending your time, very valuable time with us. So thank you very much, everybody. So who participated for the lecture, and so IESL who host this session. So for the IT people in the IESL, so I have to give our thanks. So this very valuable lecture series handled by the Professor Jayasinghe. So we will meet once again in the future, so with another session. Thank you very much, everyone.
Actually, Dr. Nalin De Silva has agreed to do some foundation lectures, right?
Okay,
so
sir.
the real deep foundation, because we cannot go as structural engineers. We cannot teach that level of sophistication, because my ranking is he's the best in Sri Lanka. So if you can listen to him and learn geotechnical engineering aspect of it, it's ideal, right? Because our knowledge is nothing when it comes to his knowledge. So on geotechnical, so you have to listen to a real geotechnical engineer, and he's the best in Sri Lanka. He agreed to do some lectures. maybe next week or week after. I think week after, not this week.
Right.
Week after. Coming week or following week, he will do some lectures. Okay.
Right. Okay, sir. Thank you very much. So we will conclude the session. So we'll meet with another session in the future.
Yes.
Right. Thank you,
Okay.
sir. Thank you for all the participants. Thank you. Good
Thank you.
night. Good
Good
night.
night.